Okay, thank you. Thank you for the introduction, Jeffrey. And well, thank you very much to the organizers for giving me the opportunity of talking in this seminar. And the research I'm going to present today is a joint work with Uwe Grimm, Yasushi Nagai, and Petra Stainova. And as you can read in the title, it has to do with arithmetic progressions happening in some infinite binary words. Well, the talk is divided into three parts. We will start with a short introduction to show you the motivation behind our research. And then we'll move to the main part, which concerns arithmetic progressions in the 2-Morse sequence. And we will finish by mentioning how the previous results generalize to other binary sequences. Well, in combinatorics of words, we are usually interested in the properties of sequences that we write on a finite alphabet. And we can interpret such a sequence as a finite coloring of the integers and then apply the theorem of van der Waals. So this theorem states that any coloring of the integers contains arbitrarily long monochromatic arithmetic progressions. So we write the integers in a row, or the non-negative integers, like here. You choose your favorite palette of colors, for example, green, orange, and purple, and then paint each of the numbers with one color. Here we have an example, okay? And now we look for monochromatic arithmetic progressions, and this means numbers of the same color that form an arithmetic progression. Here, for example, we can see an orange arithmetic progression of length 4, meaning that it has 4 elements, right? Or here we see 2 arithmetic progressions, one green, one purple, both of length 3 in this case. So what van der Waals tells us is that it doesn't matter how you paint in the numbers, you will always find arithmetic progressions of every natural length. So you will find arithmetic progressions of length 1, 2, 3, etc. And well, formally, if L and C are any 2 positive integers, then there exists a positive integer n, which depends on L and C, such that any coloring of the first n numbers, choosing colors from a palette with C different colors, will contain an arithmetic progression of length L. Well, we don't need too much notation today, and moreover, it's a standard, so I mention it quickly. We use n for the non-negative integers and n plus for the positive integers. The alphabet considered A is going to be the binary alphabet, and a finite word is a finite string of letters chosen from A, and an infinite word is a one-sided sequence of letters from A. And well, as I was mentioning, we can interpret an infinite sequence of letters as a coloring of the integers with finitely many colors. Well, if the alphabet is finite. And in this context, we can consider arithmetic progressions happening in the sequence. So if phi is an infinite word, we have an arithmetic progression of difference d and length L happening in the sequence. If there are L entries of the sequence, all of the same color, which are equispaced by d steps. And by van der Waals theorem, we know that for each positive integer L, the sequence contains a monochromatic arithmetic progression of length L. But well, if we return to our previous example, we see that there are at least 2 arithmetic progressions of length 3, the green and the purple, and the difference of the green is 3, while the difference of the purple is 4. And the theorem says nothing about the differences. So a natural question to ask is whether our sequence phi contains arbitrarily long arithmetic progressions of a fixed difference d, or whether we can find infinite arithmetic progressions in the sequence for a given difference t. Well, if the sequence considered is periodic or ultimately periodic, then the problem is a bit boring. So what we want really is to consider a sequence which is not ultimately periodic. And our first choice is the 2 Morse sequence. Okay? Well, there are different definitions of this word, but for our purposes, it's convenient to define it as the fixed point of the 2 Morse substitution starting with the letter 0. And we called the substitution theta, which maps 0 to 0, 1 and 1 to 1, 0. And then the 2 Morse word phi is the infinite word obtained under the iteration of theta starting from 0. Well, you see that theta is a primitive substitution of constant length, and it's symmetric under the operation that sends 0 to 1 and 1 to 0. And what I mean is that theta and this bar operation commute, and this is precisely what is written there in the middle of the line. And thanks to this commutation property, well, it's easy to see that the recursion on the right-hand side also holds. And this immediately shows that the nth superword, that is the image under the nth iteration of theta, is symmetric if n is even and antisymmetric if n is odd. So here, for example, these are the first superwords starting with 0. And as you can see, one is symmetric or a palindrome, and the next one is antisymmetric, next symmetric, antisymmetric, and so on. Well, and finally, before we move to the results, I need to mention that the 2 Morse word is overlap-free, and this is perhaps the most celebrated property of this sequence. And it means that, well, we cannot find a binary pattern overlapping with itself. Okay, our first result answers the question we proposed earlier. Does the 2 Morse word contain arbitrarily long arithmetic progressions of a difference t? And the answer is no. Well, we don't have many time now, so I omit the proof, but I have to say that it's strongly based on a recent result by Akiyama, Lee, and Nagai about the existence of infinite arithmetic progression in self-affine non-periodic tilings. But once we know that there are not arbitrarily long progressions, we can look for the largest ones. So we may introduce this definition. We denote by capital A, as a function of the difference t, the largest length of a monochromatic arithmetic progression of difference t happening in the 2 Morse word. Our first question is whether we can find a closed form for A as a function of t. But this seems to be difficult. We have run a computer program, for instance, and to look for the largest arithmetic progressions of several differences. And we have seen that the behavior of A is not easy to guess, and it goes up and down as n goes to infinity. So we can try to find the value of A for some particular values of the difference t. And for example, it's easy to see that A doesn't change if we multiply the difference of the arithmetic progression by any power of 2. And it's neither difficult to see that A is equal to 2 if and only if it is a power d, and the difference is a power of 2. However, we would like to obtain the value of A for other values of d. This problem of trying to determine the values of the largest arithmetic progressions was addressed earlier by Olga Parshina, and she established this result, giving the value of A when the difference is a power of 2 minus 1. Well, as I have said, the value of A goes up and down, and as d goes to infinity. However, if we look for the differences less than a power of 2, the largest value is achieved precisely when D, the difference, is that power of 2 minus 1. And this is here in this example, in this result, sorry. Well, we have reestablished this result, but our proof is based on van der Waarden's original proof, and it's different to the proof by Olga. And we further give the value of A when D is a power of 2 plus 1. So I'm going to present the result for the theorem above, but I'm not going to give the proof for the proposition below because it follows similar arguments. But before we move to the proof, I need to introduce a new substitution. And this substitution we call it capital theta, and it is a substitution of binary blocks. It sends 0 to the block 0, 1, 1, 0, and 1 to the block 1, 0, 0, 1. And the nth iteration of a letter under this capital theta generates a block of size 2 to the n times 2 to the n, okay, as in this example. And now I'm going to show you a couple of lemmas that will make clear, I think, some of the properties of this substitution. The first lemma says that the nth superblock obtained under the iteration of capital theta, if we read it row-wise from top to bottom, corresponds to the 2nth superword obtained under the iteration of the 2n more substitution. Well, the proof is not difficult, but I think it's enough if we illustrate this with an example, okay? So here, we have the second iteration of capital theta. So let us read it row by row, starting with the first, second row, third, and fourth, okay? And all of them together give us this binary word, which is precisely the fourth superword of the 2n more substitution. And now I introduce one more lemma to better understand the properties of this substitution, okay? So this lemma is about the structure of the superblocks. It says that the nth superblock obtained under the iteration of capital theta consists of only 2 types of rows and columns. And moreover, the block is symmetric under reflection in either diagonals. And finally, all the entries in the main diagonal are of the same color, of the same color we started with. And the entries on the other diagonal are also of the same color, of the same initial color, say, if we obtain the block under an even number of iterations. And they are of the other color if the number of iterations is odd. But again, let's illustrate it with examples, okay? So here we have one of these superblocks, and you can see that it has only 2 types of rows. And similarly, only 2 types of columns. And notice that each of these rows or columns are, in turn, smaller superwords of the 2n more substitution. And next, we see that the blocks are reflection symmetric under the main diagonal, as well as under the other diagonal. And finally, we see that the entries of the main diagonal are always equal to the color we started with. So in this case, all of them are 0. And the color of the entries in the other diagonal depends on the parity of the iteration. It is equal to the starting color, 0, if the iteration is even, and it changes the color, 1, if the iteration is odd. And I think with this, we understand a bit better these blocks. And the interesting thing about this construction is that it gives us for free the existence of long monochromatic arithmetic progressions of difference 2 to the n minus 1 and 2 to the n plus 1. So imagine first that we are looking for progressions of length 2 to the n plus 1. So in green, we have, in green, we see one of the elements of the progression. But since the superblocks are of size 2 to the n times 2 to the n, the next entries of the progression are precisely in the main diagonal. So in this example, n is 2. So 2 to the n plus 1 is 5. And if we count 5 steps from the first position, we end up in the next diagonal element, right? And 5 steps more and 5 more. So we have this progression. By the properties of the substitution of the superblocks, this happens regardless the parity of the iteration. So if the parity is odd, we again have this progression. And this construction gives us this lower bound for the maximum length of the arithmetic progressions of difference 2 to the n plus 1. And if we look for progressions of difference 2 to the n minus 1, it is similar. In green, we see one element of the progression. And again, since the superblocks are of size 2 to the n times 2 to the n, by steps of size 2 to the n minus 1, we end up walking across the second diagonal. So in our example, n is 2, 2 to the n minus 1 is 3. And if we count 3 steps from the first position, we end up here, and next here, there, and there, okay? However, unlike in the previous case, this time the construction only works when the block is even, because in the odd case, both diagonals are of different color. But for the previous, right. But still, even in the odd case, the previous lower bound works, because these times by steps of size 2 to the n minus 1, we walk the second diagonal, which, as you can see, is all of the same color. So we still have this progression. Well, therefore, the maximum length of the arithmetic progressions of difference 2 to the n minus 1, we have for free this lower bound, okay? And now, with all these properties, the proof we wanted to obtain is not so difficult. Recall that we want to show that the maximum length of the arithmetic progressions of difference 2 to the n minus 1 is given by 2 to the n if n is odd, and 2 to the n plus 4 if n is even. Well, we have already obtained the lower bounds, okay? So first, consider that n is odd. Since the nth superblock, nth superword of the 2n more substitution is antisymmetric, we have that the first and the last letters are different. Like in this example, the first one is 0, the last is 1. So this means that once we hit the first letter, then the progression stops. But the length of the blocks is 2 to the n, which is co-prime with the difference 2 to the n minus 1. So we end up visiting all the positions in the superword. And from here, we have that a cannot be greater than 2 to the n, okay? This is for the odd case. And now consider that n is even. Well, in this case, the superword is symmetric, and the first and the last letter, which are equal, can be elements of this progression. So assume that happens. Assume that the first and the last letters are elements of the progression. Well, then, if we want to extend the progression either to the left or to the right, the next blocks are determined, right? And also the next ones. But this is equal to that image under theta, and the word 11011 is not in the 2n Morse language. And so this gives us the upper bound we wanted. To complete the proof, the only thing we need is to show that the bound 2 to the n plus 4 is attained. And well, this is not very difficult because we have already obtained a progression of length 2 to the n plus 2 as follows. Okay, and we can extend this once to the right and once to the left. And well, then the progression stops, which gives us the 2 to the n plus 4 bound. This completes the proof, and a bit more of work shows that there are not longer arithmetic progressions for differences up to powers of 2. Okay, and well, we have already covered the main part of the talk, and now to finish, I want to give you an idea of how the previous results generalize. I should mention that Olga Parshina, she also considered generalizations, but different ones. She considered larger alphabets, and on the contrary, we considered generalized to a Morse word in the binary alphabet. We can define this new substitution, theta, okay, which is a generalization of the 2 Morse substitution. And the 2 Morse substitution corresponds to the case P equal Q equal 1. And then the generalized 2 Morse sequence is the infinite word obtained under the iteration of the new substitution starting from the letter 0. Well, many of the properties of the 2 Morse substitution are hereded by the generalized substitution, but there are some differences. For instance, the symmetry of the superwords is only preserved when P and Q are equal, or also, well, rather than working modulo 2, we need to work modulo P plus Q. Okay, but we obtain similar results. Again, the generalized 2 Morse words don't contain arbitrary long monochromatic arithmetic progressions of any fixed difference. And so we again introduce the idea of the maximum length of a progression of difference t. Well, the proofs are of the same nature. And again, we need to introduce a block substitution. Although this time is a bit more complicated. But again, under iteration, it generates square blocks of size q to the n times q to the m, where q this time is p plus q. This is an example where p and q are equal, and it has a similar structure to the original 2 Morse substitution, because, as I said, in this case, the symmetry of the superwords is preserved. And here we have an example where P and Q are different, and the symmetry of the superwords is not longer preserved. And as a consequence, for instance, we see that, well, we still have the same letter along the main diagonal, all zeros, but this is not longer true for the second diagonal, right? And with this construction, we obtain similar results to the previous ones. However, even if we have established these values of A for powers of Q plus 1 and powers of Q minus 1, we have not been able to show that among the progressions with differences less than a power of Q, the largest one corresponds to the last one. Or in other words, we have not been able to show that the values that we have obtained are the longest arithmetic progressions that you can find up to the given difference. So we state that as a conjecture. And well, the main difficulty comes from the fact that the symmetry of the superwords does not always hold, and our methods then fail. And well, I think that's all I wanted to tell you about. So thank you very much for your attention.
Thank you very much for the talk. We have some time for questions here.
Mm-hmm.
You can either type them into the chat and I'll relay them, or you can unmute yourself and just ask directly.
Hello. Do you hear me?
Yes.
Yes.
I wanted to ask whether you used the automated prover walnut for these results, which should be usable for 2 Morse.
We haven't tried anything similar. No, nothing like that. Yeah, it could be interesting, really, because I have mentioned that it's difficult to guess the value of A, of the longest arithmetic progression, as the difference increase. What what we really have is the value around the powers of 2. And if you plot the longest arithmetic progressions, what you see is something like a spectral diagram where most of the values are very, very small, and you get large values only around the powers of 2. But what happens in the middle, it's difficult. So it would certainly be interesting to try. Why not one of those automatic probers, or to obtain some results or some guess at least. Yeah.
Okay. Do we have
Thank
any
you.
other questions? Okay. If not, let's thank the speaker once again.